All right, everybody, welcome back. We are going to finish up glycolysis, hopefully, in this video. So we've powered through the first half of glycolysis and seen how we get to glyceraldehyde 3-phosphate, specifically two molecules of glyceraldehyde 3-phosphate, and we're going to see how we turn glyceraldehyde 3-phosphate into pyruvate through these next 5 steps. All right. Keep in mind, we actually made two molecules of glyceraldehyde 3-phosphate, though, so the reactions that we're describing here happen to each one of these. Very important. All right. Well, let's take a look at step 6. All right. In this one, we're going to take glyceraldehyde 3-phosphate and convert it into 1,3-bisphosphoglycerate. And you can see that net reaction right over here. Notice a couple of things. Number one, we're making bisphosphoglycerate, right? That implies that we have two phosphate groups. And we are basically converting that remaining aldehyde group that's on your glyceraldehyde 3-phosphate into a phosphoric acid ester. And we're doing it with a phosphate, right? This is going to be one of those occasions where we're actually not going to be using ATP as our phosphate source. In this case, we're going to use an inorganic phosphate. All right, so you can see now we have that phosphoric acid linkage on carbon number 1. All right, I don't know if you remember this. Hopefully you do. You might remember that using an inorganic phosphate and adding it to one of these structures. Sorry, I'm yawning. Hopefully I'm not boring you guys as much as I'm boring myself, apparently. Adding a phosphate, an inorganic phosphate, to a structure such as this, it's a very unfavorable process, right? It is an endergonic process. So we have to link it to something that is favorable. You also see the
I didn't find that contact. Who would you like to call?
My Siri started talking all of a sudden. Sorry for that. That was weird. Weirdest stuff happens to me when I do these videos, I tell you. Anyway, unfavorable energetic binding of the inorganic phosphate has to be coupled with something that is favorable. And that's where NAD plus comes in. We've mentioned NAD plus in previous chapters. We've said that it's got multiple uses biochemically. One of the most important functions it has is to be an oxidizing agent. All right, and in the process, it's itself reduced. So, really, this full reaction that you see here in step 6 is actually two half reactions that have been kind of put together, right? The first one is, as we just mentioned, we have our aldehyde group. Reacting with an inorganic phosphate. Go away. To form that phosphoric acid ester linkage. Okay. Delta G for this is going to be positive, very unfavorable. However, in the process, we're also going to have NAD plus here, and it's going to be reduced. It's going to accept a couple of H's and electrons and form NADH. And the delta G for this one is negative. Negative enough to cancel out the effects of the positive delta G for the other one. So this is really two separate reactions that have been kind of coupled together to allow this to take place. All right. Let me go back to the PowerPoint. All right. If you look at this one, this is actually a pretty cool little example. We don't go over the mechanisms for all the binding of these steps, but this is a pretty good example of how you can see these two processes kind of work in conjunction with each other, right? And I'm going to sort of talk you through this. Again, you'll want to be looking at this on a real computer or your book so you can see the full picture. All right, so what's the important part here in this particular step as far as amino acid residues? Well, if you look at it here, the E, that represents the enzyme, all right, and then it's got an SH hanging off of it. Well, what is an SH? It's a thiol group, right? Do you have any important residues, amino acids, that have thiol groups? Hopefully, you'll think for a second and you'll say, ooh, cysteine. Yeah, so this particular enzyme that catalyzes this reaction, by the way, it's called glyceraldehyde 3-phosphate dehydrogenase. Dehydrogenases act to catalyze the removal of hydrogens in a particular reaction, often using, not always, but often using NAD plus as sort of an assist or a coenzyme, I guess you could say, right? But anyway, yeah, this is all made possible by the action of the thiol group. That enables your enzyme and your substrate, which is glyceraldehyde 3-phosphate, to bind to each other, right? And this is just a good old-fashioned nucleophilic attack, right? Just like you learn in organic chemistry, right? The S has a couple of electrons it can use to nucleophilically attack the aldehyde carbon on your glyceraldehyde 3-phosphate, right? And then in the second structure right across, they skipped a step here. Once you attack, it actually makes that carbonyl oxygen into a negative O, and then your S is positive, and then you get a proton transfer from the sulfur to the oxygen. So that's how they got to the point, to the structure that they have in the second image on the right. All right, and then you see this ringed structure from above, right? That is the nicotinamide portion of NAD+. And this is the important part of it. This is the part that's actually going to be involved in your redox reaction, right? And you can see you get a reshuffling of electrons here. Basically, you see an H- from your enzyme-bound substrate. An H- leaves and goes to that ring and attaches itself. And it causes a little bit of a merry-go-round where it causes the internal ring electrons to rearrange, and that positive nitrogen up there then gets that pair of pi electrons all to itself, right? So if you compare the six-membered ring structure from this picture down below to the next one, you'll see it's got rearranged electrons, but also it's not positive anymore, right? And in the process, we said we went from NAD plus to NADH. That second structure has an extra H, and it's also got two extra electrons, so it's not negative, or it's not positive anymore. So that shows how the NAD plus gets reduced into NADH. When your H- leaves, you also have a reshuffling of electrons that happens around the O. Basically what happens is you reform your carbonyl group, right? So it doesn't show it, but something will come along and pluck that H+ off of your oxygen, most likely water, and that pair of electrons will swoop back down into a double bond. So you reform a carbonyl, right? Looking at the very bottom, that carbonyl is attached to your sulfur of your enzyme. That's when your inorganic phosphate comes in. It's got negative O's. It attacks your carbonyl carbon and basically causes that sulfur to depart or leave from your carbonyl carbon and make you form your final product, which is 1,3-bisphosphoglycerate. And then your enzyme has been recycled. It can be ready to use again. All right. 1 second, I'm going to get a drink of water. Much better. My mouth gets a little dry whenever I do this, so excuse me. Again, we see these type of interactions occur. I mean, this is what happens. Stuff like this happens literally every enzymatically catalyzed step. Certain ones are a little bit easier to use as sort of models or demonstrations of how the mechanisms work, and this is a pretty good one. So, wanted to make sure to highlight that. All right. Step 7, we're going to take our 1,3-bisphosphoglycerate that we just made and convert it into 3-phosphoglycerate. So if you look at the reaction here, what happens? Well, we have 2 phosphate groups. Basically what we're going to do is we're going to remove a phosphate group from that top carbon, the one we just put it on. We're going to leave behind a charged acetate group, or excuse me, a charged carboxylate group. And that phosphate is going to get added onto ADP. You may remember early on talking about the net overall products of glycolysis. We said there was an overall net of 2 ATP that were formed at the very end. In the first phase, right, the first 5 steps, we actually consumed 2 ATPs, which means over the phase 2 portion, we actually need to make 4. That would give us, plus 4 in the second phase, minus 2 in the first phase, overall plus 2. All right, so this is one of the steps where we actually make ATP. We make one molecule for each. We make one molecule of ATP for each molecule of 1,3-bisphosphoglycerate. Remember, we actually have 2 of these because of the 2 legs in the sort of the forked glycolysis pathway, right? So you can really think of it like this: 2 1,3-bisphosphoglycerates plus 2 ADPs yields 2 3-phosphoglycerates and 2 ATP. All right, so one of our ATP producing steps. The formation of ATP, adding a phosphate to ADP, is energetically unfavorable, right? And that makes sense. Cleaving a phosphate group off ATP is favorable. Adding one is not, right? But cleaving one off of 1,3-bisphosphoglycerate is. So, again, we see coupling of 2 different reactions here that allow for this to happen. All right, reversible reaction catalyzed by an enzyme called phosphoglycerate kinase. All right, step 3. We're going to take 3-phosphoglycerate and we're going to convert it into 2-phosphoglycerate. Well, if you think about that, really it basically looks like we're just taking a big old hand or a claw, like from a claw machine, grabbing a phosphate, plucking it off one carbon, and moving it to another one. And that's kind of what we're doing, right? We're picking up that phosphate group off of carbon number 3 and we're sticking it on carbon number 2. Notice the enzyme that catalyzes this. It's called phosphoglyceromutase. All right, mutases, basically what they do, mutases catalyze the moving of functional groups from one place in a molecule to another. So, phosphoglyceromutase is kind of the big giant claw of the claw machine that picks up that phosphate and puts it in a different spot. Step 9, getting close to the end now. We are going to take our 2-phosphoglycerate and we're going to convert it into PEP. We're making PEP. PEP is short for phosphoenol pyruvate. And here is the reaction for that. Basically what we're doing here is we're using a catalyst called enolase. And that is going to basically cause a dehydration. All right. If you look, And I actually am going to go to the whiteboard here because I can draw it a little bit better to show you. All right. Okay, so there is your 2-phosphoglycerate. We're going to convert it into PEP, phosphoenol pyruvate. Magnesium as a cofactor. And then you have enolase. All right. The important thing to remember about this one is that this is essentially a dehydration. Again, general reaction you learned in organic chemistry. What do we do in a dehydration? Well, we take away water in a nutshell, right? We have 2 consecutive carbons. One of them is always going to lose an H. One of them is going to lose an OH for a net loss of water. And then you always make a pi bond across those 2 carbons. And so this is where it's going to happen in this particular example, right? We have the H there that we lose. We have the OH there that we lose. That's water. And we form a double bond between these 2 carbons. All right? So dehydration in step 9 is going to produce phosphoenol pyruvate. And then you get to step 10, the ultimate step of glycolysis, and that is the production of pyruvate, which has been our goal all along. All right, this one's catalyzed by an enzyme called pyruvate kinase. And you'll notice here, we have another step where we're actually producing ATP, right? So we're taking a phosphate away from phosphoenol pyruvate, and in the process, we produce a ketone, and we put that phosphate onto ADP and produce ATP. And again, remember, we have actually 2 molecules of PEP. We produce 2 molecules of pyruvate and 2 molecules of ATP, right? So step 10 produces 2 ATPs. Going back, step 7 produced 2 ATPs. That's 4. Going back into phase 1, we used 1 ATP in step 3. And 1 ATP in step 1. So, overall net is 2 ATP. I'll summarize this here. Net results of glycolysis, 2 ATP, 2 pyruvates, and come on, there we go. If you look at, I want to just go ahead and look at this blue picture here. One other important biomolecule to look at is NADH, right? We also produce NADH. That's going to be important. Okay. Very good. Hope I'm not making you dizzy with all the swiping, trying to find my place. Okay. One thing you'll notice about step 10, it's getting a drink of water, sorry. It is one of our irreversible steps. Highly energetic. Under standard biochemical conditions, it releases about 23 kilojoules per mole. So, it is one of our, I think, 3 irreversible steps in glycolysis. I'm going to double check that here. Yeah, 3 irreversible steps. Those 3 irreversible steps are step 1, step 3, and step 10. All right. Pyruvate kinase is the enzyme that catalyzes this. Allosteric effects can be seen here. Pyruvate kinase is inhibited by ATP. So this is one of the other places in which we see if you already have enough ATP, you don't have to make any more. All right. And in fact, we can summarize this. We can look at some control. We can summarize the control points. We went over these, as we went over the individual steps, just to summarize them. All right. There's 3 basic control points within the glycolysis process where we really get feedback inhibition, allosteric inhibition, and they occur at the 3 irreversible steps: step 1, step 2. Step 1, step 3, and step 10. All right. Step 1 is inhibited by glucose 6-phosphate. I'm writing an I for inhibit. Step 3 is inhibited by ATP and fructose 1,6-bisphosphate. Sorry, ran out of room there. And step 10 is inhibited by ATP. All right. These are important control points, so you should make sure to be familiar with these. All right. Okay, so we said we ended up making 2 ATPs, 2 NADHs, and 2 pyruvates, right? Well, ATPs can be used directly as energy sources. NADH, a few different things can happen to those. Those can be shuttled in various pathways. Sometimes they're recycled. We'll talk more about that in just a minute. Other times they're used directly for certain other needs of the body, depending on what other deficiencies or needs you might have. And then you have pyruvate. Pyruvate has different fates. The major fate of pyruvate in animals is going to be direct entry into the citric acid cycle, right? Citric acid cycle, which we're probably not going to have enough time to get to, starts with pyruvate. All right, step 1. Pyruvate is converted into another product. And that sets the stage for formation of more ATP, right? So you've only formed 2 net ATP so far, but those pyruvates are going to be necessary to continue to make them. However, that's not the only place it can go. Pyruvate can do other things. So I want to talk about those real quick. And these are the extra slides I added because I realized they weren't in the original PowerPoint. So I wanted to pop those in real quick. All right. So in animals and plants, you can actually, in animals, you can actually get something called lactic acid fermentation, or lactate fermentation, as it's sometimes called, right? So let's say you have some pyruvate. If it enters not into citric acid cycle, but into lactic acid fermentation, that's sometimes referred to as anaerobic glycolysis. The regular glycolysis process is an aerobic process, but this is not. Remember, anaerobic processes are not going to involve oxygen. Citric acid is most definitely, citric acid cycle is most definitely, I cannot talk right now. The citric acid cycle is most definitely an aerobic process. It uses oxygen. Pyruvate, however, can enter this anaerobic process. All right, and here's a little outline of what happens here. Pyruvate, your 3-carbon pyruvate, is going to be converted into L-lactate or L-lactic acid, depending on whether that oxygen at the top is protonated or not. Right? Remember, you take a carboxylic acid, you deprotonate it, make it into a carboxylate, then you basically refer to it as an 8 instead of an oic acid. So, lactic acid or lactate. All right, this is catalyzed by an enzyme called lactate dehydrogenase, and it uses a molecule of NADH. And you'll see this is actually sort of an opposite process to what we saw in glycolysis, right? In glycolysis, you saw there were a couple of points where we had NAD+, and we reduced it into NADH. This is the opposite. We're actually oxidizing NADH into NAD+, and in the process reducing that carbon number 2 in pyruvate, right? It's a C double bond O in pyruvate, has 2 bonds to oxygen. In lactate, it only has 1, so that carbon's been reduced. So this is a redox reaction. You may ask, what is the point of having pyruvate go through this process? Well, it's all about that NAD+, right? The whole reason that this can happen is because we have to recycle that NAD+ that we used up in glycolysis sometimes. Right? If we used it up. We need to have a continuous supply of NAD+ to keep feeding glycolysis and other processes. However, if we're not getting sufficient NAD+ produced from other sources within the body, we have to start recycling some of the ones we used up in glycolysis. And this is a way for us to do this. So, if the body has a shortage of NAD+, it might send a signal to divert some pyruvate away from the citric acid cycle and to lactic acid fermentation in order to help replenish that NAD+. Lactate is really just a byproduct of this. It's not the important product here. The important product is NAD+. Now, lactate, or lactic acid if it's protonated, we do unfortunately feel it, especially when it tends to build up in our muscles. It can, make us kind of sore, which, isn't pleasant, but it happens, right? So, hypothetically, if this were to occur in a large enough amount, you might, experience some soreness because of it. This second picture, literally I took a snapshot for the next couple of pictures from the textbook because I didn't have a source to just directly insert them. Sorry about that. But it's kind of cool. You see the 2 steps where we both use up NAD+ and then replenish it, right? We see it used up when we convert glyceraldehyde 3-phosphate into 1,3-bisphosphoglycerate. But you go further down the line and you can replenish that NAD+ through this lactic acid fermentation step. So, pretty interesting. That's what happens in animals. But it's not the process that happens in every other organism. A good example of this is what happens in in yeasts, right? Yeasts can also have the need to recycle NAD+, and you can see that here, right? They use up NAD+ the same way that we would in animals, right? We use up NAD+ by converting glyceraldehyde 3-phosphate into 1,3-bisphosphoglycerate. However, in this case, You don't go through a process that makes lactic acid. You go through a process that ends up making ethanol. And this is where we get alcoholic fermentation. So, I don't know if any of you are amateur brewers or anything, but I think I even mentioned my dad used to brew wine, homemade wine, by putting a bunch of potatoes and grapes and other things in a big bottle with a bunch of yeast and then whatever else he wanted to use to flavor it. Stuck a balloon on top of the bottle and then left it to sit for however long, for several weeks, right? Basically, he was setting it up to do this reaction. And so, if you're going to be brewing a wine or brewing beer, this is the process that the yeast is undergoing, right? It's kind of similar to lactic acid fermentation, except for the fact it does involve an extra step as opposed to lactic acid fermentation. Let me find my whiteboard. There we go. Okay. So there's two reactions. All right, in the first one, you have your pyruvate. And it's going to be converted into acetaldehyde. Acetaldehyde. All right? And this is catalyzed by something called pyruvate decarboxylase. Think about that name, pyruvate decarboxylase. Remember, I said a lot of times the enzyme names will tell you its function. You hear something that's a decarboxylase, it does exactly what it implies. It removes a carboxyl group from something. And since it's pyruvate decarboxylase, what it does is it functions to remove a carboxyl group from pyruvate. So it actually goes from a 3-carbon fragment in pyruvate to a 2-carbon fragment in acetaldehyde. That carboxylate group comes off in the form of CO2, carbon dioxide. If you've ever wondered where the bubbles in beer or sparkling wines come from, that's it. It's the carbon dioxide produced as a result of this reaction. That's why when my dad would make wine, he would put a balloon on the top of the bottle. That balloon was used to catch the carbon dioxide that was coming off. And when the balloon got a certain size, he would basically know it was done because, you could use the size of the balloon to tell how much carbon dioxide had been produced. Yeah, pretty cool. You also have a coenzyme here that's going to be important. It's called TPP. It stands for thiamine pyrophosphate. Okay, so 2 major reactions in alcoholic fermentation. The first is converting the 3-carbon pyruvate to a 2-carbon acetaldehyde. By the way, I'll just go ahead and draw acetaldehyde. That's what it looks like. The last step is to convert acetaldehyde into, ethanol, which is the alcohol that's present in alcoholic beverages. And you guys know the structure of ethanol. There it is. And you'll notice this is a redox reaction, right? We have a carbon and a carbonyl group. It's got 2 bonds to oxygen. It goes from having 2 bonds to oxygen to having 1. So this carbon in acetaldehyde is reduced. That means something has to be oxidized. And guess what? That's where NADH comes in again. NADH gets converted into NAD+. So just like lactic acid fermentation recycled NAD plus, alcoholic fermentation also recycles NAD plus in yeast. This is catalyzed by, excuse me, an enzyme called alcohol dehydrogenase. Whoa, I did a terrible job with that, sorry. Very good. All right. So we're almost done. I want to highlight a couple of other interesting things. I know you guys tell me you like applications, right? How this applies to the real world, and you get a little taste of this here. I want to talk about a couple of other examples. You guys probably have heard of at some point something called fetal alcohol syndrome. Right? Of course, if you get pregnant, you're not supposed to drink while you're pregnant because it can cause problems for the growing fetus. The fetus is impacted by alcohol absorption from the mom. It can develop something called fetal alcohol syndrome, which can be deadly. All right. So here's how it actually occurs. Let's say you drink, you're drinking alcoholic beverages, you're consuming ethanol, which we just saw was the product of alcoholic fermentation. All right? Well, the same enzyme that catalyzed the production of ethanol, right, alcohol dehydrogenase, it can also catalyze the reverse reaction. So, an alcohol dehydrogenase can act on ethanol if we have consumed it and have an abundance. It can convert it back into acetaldehyde. All right. Typically, then, there's another enzyme called aldehyde dehydrogenase, I want to just abbreviate it, that typically converts this into acetic acid. Which we can, metabolize. We can metabolize acetic acid or flush it out of the system. Not really a big problem. However, here's the problem for babies, for fetuses. This guy right over here, acetaldehyde, it has a pretty big tendency to transfer across the placenta into the newborn. That particular one, not the ethanol, not the acetic acid, is the acetaldehyde. And it can accumulate in the liver of the fetus. And it just so also happens to be toxic. Acetaldehyde is toxic. It's a poison. We're not meant to have accumulations of it in our body. Now, we can take care of it, thankfully, in most cases, because we have sufficient amounts of aldehyde dehydrogenase that can convert it from toxic acetaldehyde into less toxic or manageable acetic acid. However, in a growing fetus or baby, they don't have the ability to produce as much aldehyde dehydrogenase as would be needed to get rid of this. So, they are really operating on they're going to be too low on this enzyme to handle elevated amounts of this. So, you're actually building up a poison in their liver, and that's what causes them to develop fetal alcohol syndrome. Okay? Another interesting thing to look at here is, and again, I don't know how much how familiar you guys are with your history here, specifically with how it regards prohibition. Prohibition was a time in the early, oh gosh, when was it? I should remember. I mean, I wasn't there or anything, but it was in the early 1900s. I want to say like 1920s or so. Let me look. I'll Google it. Between 1920 and 1933, there was something called prohibition that was in effect. For that period of time, the manufacture, sale, and transport of alcoholic beverages in the United States was illegal. So basically, alcohol was illegal in the United States from that period of time. Now, all sorts of people developed all sorts of ways to get around it, including people that we call bootleggers. Bootleggers would basically make their own types of alcohol through their own brewing and distillation methods. You may have heard of moonshine. That was a common bootlegger product of the day, right? Now, bootleggers, they made a lot of money with this, right? It was big business, highly illegal, but people wanted their alcohol. Now, as do many people in businesses, whether illegal or illegal, when you're making your product, a lot of times you try to cut your cost as much as possible to maximize your profit. So, they found that for much cheaper, instead of making ethanol, they could make methanol. So if you think out about it this way, whenever we make ethanol, we're using glucose as essentially the starting point, right? Because glucose has to go through glycolysis to make pyruvate. Pyruvate has to go through alcoholic fermentation to make your ethanol. And you're looking at your sources. Usually some either complex starch sources, potatoes, corn, grapes, which have not so much in the way of starch, but they have high concentrations of just individual glucose molecules, and other types of fruits as well. All right. So this would make ethanol. However, they found that by using wood as a source, they could also produce an alcoholic beverage. Now, wood is composed of cellulose, which, much like starch, has glucose units in it, right? So it's also a source of glucose. But also remember, cellulose requires different enzymes to break down the glucoses off the polymer chains than starch does, right? And so, in a nutshell, I'm going to sort of cut to the chase here. Long story short, using wood as a source of glucose did not end up making ethanol as the product of alcoholic fermentation. It ended up making methanol. Remember, this is ethanol right here, 2 carbons. Methanol is going to be 1 carbon. Pretty similar in structure, right? They will both get you drunk. They both do have some similar effects as far as, as far as the buzz and the feeling that you get. However, here's the problem. Gosh darn it. 1 second. Methanol highly poisonous. Should be no, it's not working. Okay. Methanol is highly poisonous. Here's why. Remember what I told you. We can digest ethanol. In humans, we can have ethanol. We can use ethanol dehydrogenase to make acetaldehyde. And then we can use aldehyde dehydrogenase to make we can use aldehyde dehydrogenase to make acetic acid. Okay, so this is the ethanol pathway. For methanol, it's pretty similar. Except we make a different type of aldehyde and we make a different type of acid. All right. This guy right here, this is one you might recognize. This is formaldehyde. Carbonyl with 2 H's on it. Formaldehyde. And this is formic acid. Now, we said earlier that acetaldehyde in this pathway is toxic, and that's where, having it build up in fetuses is problematic. But we can take care of this. Aldehyde dehydrogenase can convert it into a fairly benign product into acetic acid, which can then be dealt with. Here's the problem. Here's a couple of problems. Number one, formaldehyde is more toxic than acetaldehyde. It is a highly, highly toxic material, more so than the acetaldehyde. So, the power of this guy as a toxic species is higher. Also, less of it can be converted into its acid product. Aldehyde dehydrogenase works better, more efficiently on acetaldehyde than it does formaldehyde. Even when it does, though, formic acid is much more toxic than acetic acid. Formic acid is what Formic acid is what several species of ants will inject into you when they bite you, and that hurts a lot, right? Not fire ants, so that's something else. So, formaldehyde and formic acid in dual combination, that is a more toxic pairing than acetaldehyde and acetic acid. And you drink too much of this, it can make you very sick, it can cause blindness, and then eventually death. So that's bad, right? However, it's a lot cheaper to use wood than these other starch-containing starch-containing or glucose-containing supplies. So unscrupulous bootleggers would make moonshine out of wood, and it was commonly called wood alcohol. They were really making methanol. Fun fact, let's say somebody gets alcohol poisoning from wood alcohol. Do you know what the treatment for wood alcohol poisoning is, or methanol poisoning? Copious amounts of ethanol. You get them drunk with ethanol to treat them. And this can be done, orally, I guess, if they're not in too big of a danger, or it can actually be done through IV, which is probably the more common way. The reason is you try to overload the system with ethanol, so these enzymes will act upon the ethanol and not the methanol. Methanol, eventually, if it's left alone, can be flushed from the body. So, kind of interesting. All right, that wraps up chapter 17 in glycolysis, and I'm pretty sure that's going to wrap up the semester as well. We didn't get quite as far as I would have liked to in an ideal world. I would have liked to have done 2 more chapters, but I think we did pretty good, especially with the challenge of trying to do this in 8 weeks. So go ahead, listen through this, work through this. If you have any questions, let me know. Talk to you next time. Bye-bye.